Good morning, my dear friends. I hope you all are doing great today. So let us start our topic, which is Gibbs free energy, my dear friends. If you look here, it is a thermodynamic potential used to calculate the maximum reversible work, okay, that may be performed by thermodynamic system. So in simple words, I would like to tell you that Gibbs free energy is basically the amount of energy associated with the system which can be converted into useful work, my dear friends. So let's have a look here. We usually tell that water flows from higher potential to low potential, from higher potential to lower potential. When we say this statement, understand that the water at higher potential has more free energy. Yes? So water, when we say that water is at higher potential, understand that it has more free energy when it is at higher potential. So can I tell that water moves from higher free energy to lower free energy? Second example I would like to tell you. Okay, have a look here. If we talk about a chemical reaction, okay, in a spontaneous chemical reaction, okay, reactants, okay, have higher free energy and they spontaneously change into products. What is the meaning of this, my dear friends? In a spontaneous chemical reaction, reactants have higher free energy and they spontaneously change into products. That means if reactants have higher free energy, they can easily change into the products. Understand that point. Look here, water flows from higher potential to lower potential. Yes, that means the water at higher potential has more free energy. So remember that particular point, and it will flow from higher free energy to lower free energy, means from higher potential to lower potential. If reactants have more free energy, they can easily change into the products, my dear friends. Remember that point. So this is all about the Gibbs free energy. So you might have noticed that here, it's a thermodynamic potential used to calculate the maximum reversible work that may be performed by a thermodynamic system at constant temperature and pressure. If we talk about a thermodynamic system now here, my dear friends, look here. If I take one cylinder here and I will take on one piston, okay, and let us suppose this is the external pressure and here we have gas, my dear friends, and the pressure due to the gas is internal pressure. If the internal pressure of the gas is more than external pressure, let us suppose P internal is greater than P external, which means this gas, the pressure of the gas which is present in the cylinder has higher free energy. So this guy has higher free energy, my dear friends. And P external means whatever the pressure is from outside, that is less only, so it has low free energy, low free energy. What is the meaning? If P internal is greater than P external, internal pressure is greater than external pressure, it means the gas which is present here inside the cylinder has higher free energy, okay, and the external pressure due to atmosphere, yes, has lower free energy. Then what will happen, my dear friends? Okay, the expansion will happen. So here work of expansion will happen, will take place. because P internal is greater than P external. Okay? Or we will say, or the gas in the container, we can say, or cylinder has more free energy and can easily do the work of expansion. So my dear friends, please remember this. I hope you have understood my term. If the rock is at the higher potential, yes, a slight push is required and it will roll down to the foothill, from the top of the mountain to the foothill, from higher potential to lower potential. And higher potential here means the high free energy. During osmosis process, my dear friends, what happens? Water flows from the higher concentration to lower concentration through semi-permeable membrane. That higher concentration of water means it will have the higher potential, higher free energy. So remember always that a reaction will be spontaneous if it has a higher value of free energy, my dear friends. Higher value of free energy in the sense means it should be capable of doing the work. Yes? So remember that, my dear friends. Please make note of this. Dear friends, let us see what is the symbol for the Gibbous free energy, my dear friends. So if we talk about the symbol, okay, representing Gibbous free energy, is G. So we will represent the Gibbs free energy by symbol G. Okay. So change in Gibbs free energy. Change in Gibbs free energy. Here I am talking about change, my dear friends, is represented by delta G, my dear friends. Okay. Now let us see the mathematical expression for the change in Gibbs free energy, my dear friends. Mathematical expression for change in Gibbs free energy at constant temperature, my dear friends. So what is the mathematical expression for change in Gibbs free energy at constant temperature, my dear friends? Have a look. It is delta G is equal to del H minus T del S. So this is the mathematical equation for the Gibbs free energy. Okay. So now what is delta G? Everybody knows it is basically the change in Gibbs free energy. It is this term. Delta H, everybody is aware, this is change in enthalpy. This is here change in enthalpy. T is basically the constant temperature. So it's constant. Delta S, you are aware now, it's a change in entropy. Change in entropy. So this is our mathematical expression for the change in Gibbs free energy. And what is the SI unit of delta G? SI unit of Gibbs free energy is joules. So this energy is measured in joules. And later you can do conversion of joule into kilojoules, kilojoules into calories. It all depends upon that what is the requirement in a particular question, my dear friends. So please make note of this. Dear friends, let us talk about now Gibbs free energy change and the spontaneity of a physical process or chemical reaction. Spontaneity is basically related to the spontaneous reactions, my dear friends, that they have a potential to take place by themselves without the help or assistance of the external agency. We have read that topic in detail. Now let us focus right out here. First of all, we know that the mathematical expression for Gibbs free energy change. Gibbs free energy change. So what is the mathematical expression for the Gibbs free energy change? We are aware about this thing. Delta G is equal to del H minus T del S. So I can say that mathematical expression for Gibbs free energy change at constant, you can say at constant temperature and pressure, my dear friends. Okay. So let us go further. Let us call it as equation 1. In previous class I told you the spontaneity of a reaction in terms of delta S total, that is delta S universe, my dear friends. So have a look here. As we know, delta S total is equal to delta S system plus delta S surroundings greater than 0. We know that delta S total, this delta S total, my dear friends, is basically delta S universe. So this is the entropy change of the universe is equal to sum of the entropies of system and surroundings. If their value is greater than 0, understand it is for the spontaneous process. So remember, delta S total equal to delta S system plus delta S surrounding greater than 0, okay, for a spontaneous process, or we can say spontaneous reaction, okay. So my dear friends, for a spontaneous process, okay, or we can add on here, as we know, for a spontaneous process, that is better. Spontaneous process or a reaction. Let us erase it there. So now, my dear friends, you are aware that delta S total, okay, should be greater than 0 for a spontaneous process. But our topic is Gibbs free energy change and spontaneity, my dear friends. So we have to understand the spontaneity in terms of delta G, not in terms of delta S total. But we will take help of this particular equation and find out the delta G, my dear friends. So let us understand this entire process. Let's call it as equation number 2, my dear friends. Okay. I told you previous time, my dear friends, if I take out this delta S surrounding here, this delta S surrounding, let's take out this delta S surrounding. That is basically the entropy change of the surroundings. Okay, it's equal to, okay, previous time I told you that delta S system is equal to Q upon T. Yes, then delta S surrounding will be minus Q upon T. And we know that this process takes place at constant pressure. So in place of this Q, I can write down QP and here also QP. Then in place of QP, we know that heat absorbed at constant pressure is equal to delta H, my dear friends, of a reaction upon T. And this will be equal to minus delta HR upon T. Yes? So if this is an entropy of a system, it will be equal to delta HR upon T. And entropy of surrounding will be minus delta HR upon T. What is the meaning of this? I want to tell you. Let us suppose heat is absorbed by the system, okay, at constant temperature. When system is absorbing the heat, at the same time what will happen, my dear friends? The surrounding will lose the heat. Yes, if system is absorbing the heat, the surrounding will lose the heat. Now if reverse is happening, if surrounding is absorbing the heat, then system will lose the heat. So it can be like this also, my dear friends. The same thing can be like this also. Delta S system is equal to minus QP upon T is equal to minus delta H RT. Right now the system is losing the heat. Right now system is losing the heat. When system is losing the heat, obviously the surrounding, if we talk of surrounding, it will gain the heat, my dear friends. So it will become the expression will be like this. Once again I am telling you, my dear friends, if system is absorbing the heat at constant temperature, okay, then surrounding will lose the heat at constant temperature. If reverse is happening, if system is losing the heat, minus Q means loss of heat, then surrounding will absorb the heat. So let us suppose, my dear friends, in this particular process, if I will tell you that the surrounding is basically, come on, absorbing the heat. If surrounding is absorbing the heat, which expression I will use? The surrounding is absorbing the heat. I will use this expression, my dear friends. So I will use here Qp upon T. Here this surrounding is absorbing the heat. Then what will happen, my dear friends? Look here. You try to understand. Surrounding is basically absorbing the heat at constant temperature. At the same time, system will lose the heat. The loss of heat by the system, will be equal to the heat gained by the surroundings. That means these two values will be equal, my dear friends. I can tell you like this. Okay, delta S system, entropy of the system, okay, that is minus actually here, is equal to entropy of the surroundings, but their value will be same. Yes, here the entropy will increase and here the entropy will decrease, my dear friends. So that is the only thing which is happening right out here, my dear friends. Okay, we can also write down this expression like this in terms of these values. Okay, what is this all about? This is for the system and this is for the surroundings, my dear friends. So these two expressions will be also equal. So I will be having here minus del H system upon T is equal to del H R surrounding upon T. So these two expressions will be also equal. So now, my dear friends, we know that this Qp upon T is equal to delta H R surrounding by T. So I can write down delta H surrounding upon T. And we know that this delta H R surrounding upon T is equal to minus, look here at this expression, you look here, delta H surrounding upon T is equal to delta H system upon T. So I can also write down it's equal to delta H system upon T, but here the value will be minus, my dear friends. So finally you understood that delta S surrounding can be related to delta H surrounding upon T, or it can be related to minus delta H system upon T. Surrounding is basically, endothermic, yes, and system is exothermic like that. Or we can say that the surrounding is basically absorbing the heat and system is losing the heat, my dear friends. That is the only thing. Now after learning this entire process, let us go further and we will substitute the value of delta S surrounding in this equation number 2nd. And what we are going to get, have a look. So let us try to understand it, my dear friends. Substitute the value of delta S surroundings in equation number 2nd. Substitute the value of delta S surroundings in equation 2nd. We get. So let us see what we are going to get. Have a look here. We have an equation number 2nd, delta S total, that is of universe, entropy change of universe or total entropy, that is delta S system. Now in place of delta S surrounding, my dear friends, we have this expression now. What is this expression equal to? Look at the final expression here. We want this expression actually. So delta S surrounding is equal to minus delta H system upon T. So I will write down here formula is plus, and this delta S surrounding is finally equal to minus delta H system upon T. So once again I will tell you, delta S surrounding is equal to Qp upon T, heat absorbed by the surrounding at constant temperature. That's equal to the enthalpy change of surrounding at constant temperature. Now enthalpy change of surrounding at constant temperature will be equal to, okay, the minus of del H system upon T, because if this guy is absorbing the heat, then system will lose the heat. That means the magnitude, quantity will be same, but only things will be different, like one is absorbing and one is losing, but quantity of the energy will be same. If this guy is absorbing 10 joules of energy, then this guy will lose 10 joules of energy. Only sign will be different, my dear friends. So in place of now delta S surrounding, I will use the final expression here. So here I am using the final expression minus del S system upon T. So I will get here del S total is equal to, my dear friends, del S system, okay, plus minus only, so it is del H system upon T. So before I go further, my dear friends, let me mention here about this particular equation. If you focus right out here, you will find out this is basically your delta G system, delta H system and delta S system. Let us relate it only to the system. Please focus right out here and see this particular thing. So you can mention that thing. Now look here, my dear friends. If we take LCM and all those things here, finally what we get here, you will get delta H total is equal to, this T will come off here, that is T del S system minus del H system upon T. Then finally this T will come here, you will get T del S total is equal to T del S system minus del H system, my dear friends. So obviously we will further go into this particular derivation and all. Please make note up to here. Please make note. Dear friends, now we are finally with T del S total is equal to T del S system minus del H system. So that is our expression, my dear friends. And if we go back, look here, my dear friends, try to focus here. You will find out that del S total is equal to del S system plus del S surroundings, and this value is greater than 0, then it's a spontaneous process, my dear friends. So we are using the same expression here. We are using the same expression here as well. So we can add on here. Either you finally add on like greater than 0, or you can start adding from here also. It's your choice. So avoid the confusion, my dear friends. We know already that this del S system plus del S surrounding is greater than 0. Either you can add this 0 at the end, or you can add it from here also. Yes or no, my dear friends? Okay, you can add as greater than 0, greater than 0, greater than 0, and finally this one. It's not necessary, but for your understanding I am telling you that you can either say this is greater than 0 at the end, or right from the beginning you can mention everywhere. Yes? So my dear friends, finally we have this particular expression. Once again I am telling you, this expression was greater than 0, it's a spontaneous process. So I added the 0 everywhere. So greater than 0, and finally this expression. Now what I am going to do, have a look. So we know that this is a spontaneous process, my dear friends. So let us further understand how we can represent that particular equation here. Have a look. Have a look at this particular expression finally, that is T del S total is equal to T del S system minus del H system is greater than 0. Greater than 0 means spontaneous, correct? Now look here, my dear friends, what I am going to do. If I take this expression, my dear friends, okay, I can write it like this also, del H system. What is del H system? Minus. So this term is minus, so I will write down minus outside. So del H system is minus, so minus only. But this guy is plus here, T del S is plus. So I will mention here minus, because minus into minus is plus. So this guy will become plus, my dear friends. T del S system is greater than 0. Once again I am telling you, I have rearranged this equation. I took delta H in the front, but delta H is negative, so I mentioned negative. And I have taken T del S after, like this here, and T del S is positive. So this thing is positive here, my dear friends. So minus into minus will become plus only, my dear friends. Please remember. Now this is your expression. So finally T del S total is equal to minus of del H system minus T del S system. Now look here, my dear friends, del H system minus T del S system, look here, del H system minus T del S system is equal to delta G system. Please try to understand this expression. Yes? So my dear friends, let us call it as equation number 3rd for time being. Let us see this expression, my dear friends. Focus on this expression. Del S system minus T del S system. This expression is equal to delta G. Okay? Substitute the value of del S system minus T del S system in equation 3. We get. So let us put this value in equation number 3. What is the value of this del S system minus T del S system? We know that this guy is equal to del G system. Have a look here. That is our first equation. It's equal to del S system minus T del S system is equal to del G system. So it's equal to del G system here. So I will put it in equation number 3. And what are we going to get? Have a look, my dear friends. So have a look here, dear friends. So we will have T del S total is equal to, my dear friends, in place of this thing now, this entire thing except minus. Minus is outside. In place of this particular thing, I will write down now, in place of this thing, I have to write down del G system. So it will become equal to, my dear friends, minus will remain there. This entire thing will become del G system. Del G system is greater than 0. Okay. Now I can also write down this as, okay, let me write down del G system is greater than 0. Let's call it as equation number 4. That is my final equation, my dear friends. Now I can discuss about Gibbous free energy change and spontaneity in terms of delta G. Please remember that. Look here, my dear friends. This expression I can also write it like this. Have a look. If minus delta G is greater than 0, what is the meaning of this? Have a look here. You try to understand the meaning of this. Minus delta G greater than 0. Keep the minus here. So in place of delta G, if I write down some negative value means minus 10, minus 20, whatever it may be. Let me write down here minus 1, for example. Yes. So is greater than 0. Minus into minus is what? Plus. So obviously 1 is greater than 0. I hope you are understanding or not. That means keep this minus outside only. Bring the value of delta G as what? Yes, minus value. You can even keep here as minus x. And here you will get plus x, and obviously the plus x will be greater than 0, just like that, my dear friends. Now, after that, my dear friends, if I want to write down, can I write down minus delta G system is less than 0? No, I cannot write down. Why? Because I kept here it as minus 1, and it will become 1. 1 is not less than 0, so this is not possible. Then what can I do, my dear friends? Have a look. I will write down this above. I hope you are understanding. This is not possible. So what I am going to do, have a look. I can write down now, in place of this, I can write down delta G system is less than 0. No problem. Because what was the value of delta G? I kept minus 1. Obviously minus 1 is less than 0. I am not using the negative sign here. So minus delta G is greater than 0, that we can understand, because this delta G value has to be negative only. Then only it will be greater than 0. Yes? But if I write down delta G is less than 0, obviously at that time this delta G is negative only, that we know. But this minus 1 is obviously less than 0 only, that is true. So now I have changed this expression. This expression, I have changed it to this expression. Let's call it as equation number 5. Okay, and remember this delta G is negative only, keeping this minus outside, and obviously this thing is also negative only. Remember, delta G is negative here, correct? Now, my dear friends, we will write down three terms here in terms of delta G. When delta G is less than 0 means what? Negative. Three conditions we will write down here. So, delta G, negative, less than 0. Okay? So, for any chemical reaction where delta G is less than 0, because I kept it here as -1, let us suppose, and -1 is less than 0, so obviously delta G is negative. Okay? Delta G is negative for a spontaneous reaction, my dear friends. So finally, this is my expression. If the delta G value is negative, okay, it is a spontaneous reaction. So finally, delta Gibbous free energy change and spontaneity. So we reach into this conclusion, my dear friends. Yes, but here if you look at delta as total should be greater than 0. But delta G should be less than 0 for the spontaneity of the reaction. It is the same expression, but I just have, yes, taken out this minus sign, then the things will have been reciprocated. Okay, it was greater, minus delta G was greater than 0 and delta G is less than 0. The expression is, almost same. So obviously delta G is negative, then it's a spontaneous process, my dear friends. Please make note of this. Dear friends, now let us understand the spontaneity in terms of the two things. One is delta S total, that is delta S universe, and delta G system. I hope you have already understood the previous things, so let us take on. Before we go further, I will take on three things here. One is spontaneous reaction I will take on. Then I will take on reaction at equilibrium. Okay. This term you will understand in detail in the chemical equilibrium chapter. But here, let's have a little idea about it. And then I will talk about a non-spontaneous reaction. Non-spontaneous reaction. So my dear friends, if we have a spontaneous reaction, I told you, okay, it takes place, we know that it takes place by itself without the help of an external agency. I have already discussed this thing in detail. And what is non-spontaneous reaction? Okay, it requires large amount of energy. It requires large amount of energy. Amount of energy to take place. To take place. It does not take place by itself. It requires large amount of energy. What is the reaction at equilibrium? At equilibrium, what happens? Okay. Here, at equilibrium, or we call it as saturation point. At equilibrium or saturation point. You will understand it in much detail in the chemical equilibrium chapter, but here let's have some little idea about it. At equilibrium or saturation point, okay, the rate of forward reaction, okay, becomes equal to rate of backward reaction. Okay. So my dear friends, reaction at equilibrium. What is happening at equilibrium? The rate of forward reaction becomes equal to rate of backward reaction, which means, look here, the reactant will be there. It will change into the product. Or let me take one actual example here. Let's suppose we have nitrogen gas. It interacts with 3 times hydrogen gas. And now look here, my dear friends. It gives P2 times NH3, ammonia gas. So if I say that this reaction is at equilibrium, my dear friends, because here the reactant will change into the product and the product will change back into the reactant. Look here, this arrow will tell you reactant is changing into product and product is changing back into the reactant. So understand this, these arrows will tell you that it is at equilibrium, my dear friends. So what is the total change in this process? The total change is 0. Because reactant and products, reactants are changing into products and products are changing back into the reactants. That we call as equilibrium. So that means what happens here? There is no total change. Let's suppose I am going one step forward, one step backward. What is the total change? 0. So total displacement is 0. It's the same thing. When rate of forward reaction means speed of forward reaction, that means with which speed reactants are changing into products, with the same speed products are changing back into the reactants. That means the total change in this particular process will be 0, and we call it as equilibrium, my dear friends. If we talk an example of a spontaneous reaction which takes place by itself, let us take acid-base reaction. Let's take HCl. We have an acid. Let's take a base, NaOH. We'll get a salt and we will get a water. Let us take an example of a non-spontaneous reaction which requires large amount of energy. Let's take calcium carbonate. It requires large amount of heat energy to break it. You'll be getting calcium oxide plus carbon dioxide, my dear friends. So now my point is that the criterion for the spontaneity, remember always, I'll write down here for this spontaneous reaction. My point number 1. For spontaneous reaction, delta G will be always minus. So delta G is negative for a spontaneous reaction. Mention that here. Second point here. This is a reaction at equilibrium where reactants are changing into products. Products are changing back into reactants at the same speed. Yes? So now look here, my dear friends. For a reaction at equilibrium, delta G value will be always 0. Remember that. So free energy change will be 0 at equilibrium. But when we look at the non-spontaneous process, it requires large amount of energy. So this process requires large amount of energy. So delta G value, my dear friends, here will be positive. So now you understand, my dear friends, delta G will be negative for a spontaneous process. Remember that? Delta G will be 0 for the equilibrium. And delta G will be positive for the non-spontaneous process, my dear friends. Remember these points. Let us understand it in terms of now entropy, total entropy of the universe. Yes? So let us understand it here. Can you focus it here? So remember, delta S total, that is the entropy of the universe, is equal to entropy of the system plus entropy of the surroundings. And remember, this is a spontaneous process. We already know that for spontaneous process, this value has to be greater than 0. That means delta S total will be greater than 0 for a spontaneous process. Let's come here. So delta S total is equal to delta S system plus delta S surroundings. It will be equal to 0, my dear friends. Here it is greater than 0 for a spontaneous process. But here delta S total is equal to 0 for a process at equilibrium. For the process which is spontaneous, delta S total is greater than 0. That means positive. But delta G is negative. Remember, delta G is negative for spontaneous process. But delta S total is greater than 0 means positive for the spontaneous process. But here both are same. Here delta G is 0. And delta S total is also 0, my dear friends, for the process at equilibrium. Okay? Finally, at the end, when delta G is positive for a non-spontaneous process, then delta S total will be negative. Yes? So delta S total is equal to delta S system plus delta S surroundings is less than 0, my dear friends. In short, if we tell now about the entire thing, okay, if we try to summarize it, you will find out delta G is negative for spontaneous process, but delta S total is positive, greater than 0. Delta G is positive for the non-spontaneous process, yes, but delta S total is less than 0, that is negative for the non-spontaneous process. At equilibrium, both are equal. That is equal to 0. Delta G 0 and delta S total also 0. I hope, my dear friends, you have understood the spontaneity of a chemical reaction or a process in terms of delta S total and delta G system, my dear friends. Here you should mention this delta G as a system. Delta G system, delta G system and delta G system. You can even summarize it now, my dear friends. Okay? Before I would like to take the leave, I must tell you one thing, delta G is negative for the spontaneous process, 0 for the process at equilibrium, and positive for the process which is non-spontaneous. And delta S total is positive for the spontaneous process, 0 for the equilibrium, and negative for the non-spontaneous process. Please remember these points because they are very much important for the competitive examination point of view. Okay, with this particular point, I would like to take the leave, and tomorrow will be our last topic of this particular chapter, thermodynamics. Have a great time. Yo-yo.